review this. You know, what are all the pieces that we need to review so we don't forget something? Because guess what? Once we've approved it, once Ameren, Illinois has approved it, guess what? Then we have to figure out what we have to do to fix it if it's causing issues, causing reliability issues on our system. So we really had to do some reviews. We put together a team of about 20 people. Cody Davis was a very integral part of this review process that we put together as a team. And hopefully we got it's a learning every day. It's a new turn. And I know Cody talks about how many versions of this review process we've done, because as we go, we're learning as we go too, because this is pretty new stuff for us in Ameren, Illinois. Okay, we're going to take who's introducing Cody? Angie White.
Hi, I'm Angie White, Key Account Executive for Ameren, Illinois. I have the pleasure of introducing the next speaker, which Brian has already mentioned. It's Cody Davis. Cody Davis graduated from SIU Edwardsville with a bachelor's degree in electrical engineering in 2014. He has worked for Ameren for 3 years, focusing on project design, low voltage planning, and system analysis in the Peoria area. Please welcome Cody Davis.
Technical difficulties, unsurprising.
Did it get turned off?
Well, we got a dead battery. So like I said, my name is Cody Davis. I work out of the Peoria office for Ameren, Illinois as a district division engineer. We're kind of the umbrella that catches all of the various problems. We do specific structure design, plan new projects, system planning, system analysis, and those types of things. And today, we're going to focus on the interconnection process and what we do to study the effects of these big 2 megawatt solar installations as they come on our system. So as has been previously mentioned, Illinois is a great, rapidly growing solar market because of all the various incentives. 30% federal tax credit right off the top. There's a $250 per kW inverter rebate for smart inverters on these community solars. As they get their subscribers, there's the renewable energy credits that are coming. There's the bill reductions from net metering. So there's all kinds of incentives that are driving all of this solar investment. And that's great, but it causes a lot of complications on the distribution system for us. Traditionally, power flows one direction. Starts at the generator, goes to the transmission system, goes to the distribution system, goes to your house. Things are referred to, it's upstream of this, we're downstream of this. I'm fed from this substation. Kind of imagine it like if you had a town with a street that's been a one-way street for 100 years. Now all of a sudden the city planner says, this will be a lot better and more efficient if we make this a two-way street. Well, that's fine, and maybe it is, and in solar's case, of course it is, but it's gonna be some problems. People have to get used to it. The linemen in the field have been working off of power flowing in one direction their whole careers. All of our devices are set up to look one direction. There's some devices that can't even handle backfeed. So we've got a lot of those types of problems where it creates a lot of conceptual issues for us in addition to the specific system issues that we're going to talk about. Creates a lot of complexity and requires some change on our side and some change in our thought process. Oh, cool. So here's the kind of the overview of the traditional power system. Generation to transmission to distribution to the house. And this whole paradigm kind of shifts as we get more and more solar deployed where power doesn't necessarily flow down from the substation out to somebody's house. Maybe it flows from the solar installation 5 feet over to their house instead, or backwards, or in all kinds of very interesting and challenging directions. There are benefits though for both the utility and the generation owner. You get a lot of voltage improvement during heavy loads. You're offsetting a lot of your peak loading because now you've got generation, so you don't have to source as much. You've got less voltage drop because you're not coming from a power plant 100 miles away. You're coming from the solar array a couple miles down the road. So that helps a lot with line loss reduction, more efficiency. It gives us less voltage drop. There's also in the future with these smart inverters, the utility will have control of output and power factor so that we can use these smart inverters to increase our voltage regulation and provide more stability on the system and offset some of our capacitors and other types of equipment that we would have to install otherwise. Also, as it offsets peak feeder loading, so we've got more capacity to serve load without having to install more generation or upgrade any of our facilities just by virtue of having these on our system. So there are a lot of benefits for us. That said, there are a lot of drawbacks, the main one being that it's a lot more complicated. We can't control the production that they have on that system. If they need to turn it off for a couple hours in the middle of July when it's 100, we have no control over that. It's their unit, we can't touch it. We can turn it off if we have to, but we can't ramp it up. And we can't say you need to be on. So that creates a lot of problems. It's sort of like the traditional generation problems where it's not dispatchable. So we have to match to what their output is. It makes the modeling and analysis a lot more complicated because now instead of having one peak load case where everything flows how we think it does, now all of a sudden, well, maybe it was cloudy when it was 98 and the solar wasn't putting out what we thought it was, or maybe it was sunny and we were at 8 o'clock on a Friday morning and nobody's home. We've got a lot more generation than we do load. So it creates a lot of complexity for us because the output is not certain. It follows a probability curve just like everything else, but there's a lot of planning issues that come up for us in this process. Also, as I mentioned, there's some operational issues just because we don't have any experience dealing with these on distribution. Most of the ones we have are behind the meter, 10 to 15 kW, a couple of bigger installations, but as Brian said, we've never put a 2 megawatt system on distribution before. The distribution linemen are not used to dealing with generation being right next to them and potentially feeding backwards. And sometimes it takes them a little bit to get used to it. Division engineering, system engineering is the same way. Power's flowed the same way for 100 years. And now all of a sudden, there's these more complicated, uncertain generation items that nobody's dealt with coming online saying, does this cause any problems? Well, how should we know? So we've kind of developed this process that says, okay, here are the things we're gonna look at, here are the potential problems that we think we're gonna find, and here's how we're gonna fix them as they come up. One of the main drawbacks for solar specifically, and not wind, is that the peak generation for solar doesn't line up with the peak load. So your peak generation for solar, it's noon, the sun is glaring, nobody's home. Peak load usually happens 5, 6, 7 o'clock. People get home, they turn the air down, air conditioning ramps up, appliances ramp up, lights all come on. But especially in certain times of year, that peak load, the sun's already going down or is past the angle where the solar is going to get most of its output. So there's a mismatch between what the generation actually adds and where that load is. This is the curves that go along with that. So you see on the left, the top is the demand curve, which is how much power is actually being used, versus the two bell curves of the generation. And the actual peak is a couple hours after that peak solar generation. So if you add those together, you get on the right, it's been referred to as a duck curve, where it offsets your load for the main part of the afternoon, but you still have that huge peak at like 6, 7 o'clock when people are coming home, but the solar's not producing like it was at noon. So it does have some peak offsetting, but it's not a one-to-one. 2 megawatts of solar doesn't take the need for 2 megawatts of generation off of our system. like a lot of people kind of think it does. Power is very time dependent. When you use your power is a lot more important than how much is connected. So we talked about a little bit about some potential system problems. Reverse real power flow through equipment that can't handle it. A lot of devices have been set up for 100 years to look one direction. Specifically voltage regulators and a couple of protective devices where it's saying, okay, I have my source on one side, I have my load on the other side, I behave this way, and everything works. Well, if you're feeding backwards, all of a sudden, you're regulating in the wrong direction, and your controller doesn't know what to do. Also, as we get more and more solar, we can have overloaded equipment because of this reverse flow. Traditionally, your equipment is sized higher around where your load's at and close to your source. So around the substation, you've got a lot more capacity than you do 5-6 miles away from the substation. If you put all of your generation a couple miles away from the substation, you might overload that conductor, whereas it doesn't have enough actual load coming through it normally, but when the solar is all pushing, you're overloading that conductor. So that's another thing that we look out for. Flicker issues is a big one. We have voltage regulating equipment, and traditionally there's a 30-second delay at the feeder at minimum to respond to a voltage event. So if you've got a lot of load coming online, it takes about 30 seconds to react and to step that voltage up so that you maintain a good voltage to your customers. Well, the solar hits a cloud, and all of a sudden the output drops from 100% at 2 megawatts to 20%. There's a huge voltage change, especially as you get further and further out from your system. And it takes us 30 seconds to respond. So one of the things that we look at is, what is that percentage change, and is that low enough to be acceptable for our customers? And I'll go through a little bit more in detail here in a second. Over voltage and light load is also a problem, where you've got maybe on some of the more rural feeders, which is where most of these are going because land is cheap, out there away from all of the customers, where you've got a bunch of farm fields where they can get land for really cheap. While you're further away from your load, you're further away from all of our equipment, you're getting out into where you might start to see voltage problems because you've got more generation than you do load. So that's one thing we really look for. The general theme of this is the further away you get from the substation, the more problems you start to have. System impedance is really the driver for a lot of the over voltage and flicker type of problems. One other issue, system protection coordination issues. Not as much with solar, but with some of the other DERs where you're adding fault current coming from weird directions. Our protective devices are looking one direction, source bushing, load bushing. Well, if you've got like the wind farm specifically, now you've got fault current going the other way, it starts to create some problems for us. Less so with solar because the contribution is not as high, but it is something we still look out for. So here's the kind of steps that we look at in our actual analysis process. First, we look at specific interconnection requirements, that's mostly equipment. Determine our extreme load cases. We look at the system in 2 extreme cases for solar. System peak load as the one, and then what's called the solar minimum load. We'll hit that a little bit in a second. We set up our models, we run our power flows, we run through the flicker analysis, and then we check our system protection and make sure our fuses and reclosers and breakers are all still going to behave how we think they will. And basically through this whole process, we treat these 2 megawatt solars like we would any other customer. We now evaluate their impact on the system, run through our steps, make sure they're not going to have negative impacts on the rest of our customers. We're not trying to throw up roadblocks and say, whoa, we don't want this, you can't do that. We're treating them like we treat everybody else. We think that's pretty fair. So interconnection requirements, we are putting SCADA-capable metering on the solar so that we know exactly what their generation is and can queue it on demand so that our dispatchers know what's going on, so that if we start to see flicker problems or over voltage or things like that, we know what the solar output is. If it's off, we know about that too. It gives us a lot of information, helps us with our planning too, because we know exactly what the load was when our system peaked, lets us kind of offset that and determine what our actual load is in regards to system impact. We have a 3-phase gang operated disconnect switch on their side. That's just so we can turn them off if we need to, if we're doing switching, if we're gonna cause some problems, if we need to isolate something, we can go in and disconnect them for as long as necessary in an emergency so that we can restore the system to its regular configuration. The non-islanding inverter, basically, so if they lose power, it disconnects the solar from the system so that it doesn't start backfeeding and cause problems for our guys who are working on it. And then no objectionable system impact. That one's really the key here. Those 4 words end up being a couple hours worth of engineering analysis times 180 applications. So that's kind of what we're going to hit in a little more detail. So we've determined our extreme load cases. Again, summer peak and what's called solar minimum to identify the potential problems. At the extreme cases, that's when you find out what the problems are. Summer peak is mostly for flicker issues because you've got a lot more voltage drop because you've got more load. So your currents are higher. The further out you go, the lower your voltage gets. If you throw a generator up there, it improves your voltage. But if it drops offline, then your voltage swing is a lot higher because there's a lot more drop than there was before. So that's what we look at in the peak case. And then we also look at what's called the solar minimum case between 8 a.m. and 6 p.m., not the absolute minimum. We're not modeling the system at 1 in the morning, saying, oh, it's not going to work at 1 in the morning. The solar's not on. So we try and limit it to the time window when it's going to be applicable. It's usually, we're looking for reverse power flow issues, over voltage, and occasionally some flicker, depending on what circuit it is. So our model setup, we do a lot of modeling. We model all the feeders off the same substation. Any feeders that could be impacted by auto transfer schemes. The past couple of years, we've got a lot of these auto transfer schemes where if we lose a feeder, it'll auto transfer half the customers over to another feeder, which is great, but it adds complexity. So we have to make sure that in any configuration that we can achieve with these auto transfer schemes, that the solar is going to work. It's not going to cause backfeed, it's not going to cause overvoltage, it's not going to cause issues for the rest of our customers. We have, again, separate models for the system peak and solar minimum cases so that we can identify these issues at the extremes. The big one here for us is verifying that the impedances are right. Substation impedance, so we can model impedance from the transmission source, conductor impedance on the line, because the impedance is really what drives a lot of these problems. The higher your impedance is, which is the further away you get from the substation, the more you start to see overvoltage, the more you start to have extreme flicker problems, the more you start to see issues. Usually more than 5 miles outside the sub, you're gonna have a lot of flicker. And that's not something that we allow, depending on what the feeder is. And then again, make sure our regulators are set up for what's called a cogeneration mode. So regularly they're fed from one direction, but they can be fed from another weak source, which would be the solar, and the controller knows how to handle it. So in the power flow analysis, we run our minimum model. We look for reverse flow through regulators. If we need to, we can upgrade the controllers so that they have this cogeneration mode. Regs installed like 40 years ago are not ready to handle backfeed from solar. So a lot of times we're upgrading to one of the newer types of controllers that can handle it. So we look for overloads, reverse flow, and overvoltage. Overvoltage probably being the most common. So then we run our analysis in normal conditions. We rerun it for the loss of protective devices. Basically, the same theme as before. Anything that can happen, we want to make sure the solar doesn't cause negative impacts for our customers. At the end of the day, we are responsible for maintaining a strong system for our customers, and if the solar conflicts with that, that's when we start to have issues. Those are when we start to say, no, well, we need to do these things beforehand. We're always looking out for what keeps a solid and reliable system for the customer. And then again, we run our analysis with some of the commonly used feeder ties under contingencies if we need to. So I've said flicker a couple of different times. Our flicker process we run in 4 different cases. We run at the peak load and at the minimum load, and we go from 100% output to 0%. That's a little bit extreme, but we'll make a couple of different conservative assumptions in here just to make sure that we're not going to have these flicker types of issues, because these are very difficult to actually fix once you put it on the system without spending in the 7 digits. So those cases, you might think going from 0 to 100 and 100 to 0 would have the same results. Sometimes it does, but a lot of times the regulator ends up at a different spot when you start. And so there's some discrepancy between cases. We just want to make sure we're catching all of the possibilities. So what we're looking for max percent change at any important locations on the feeder. So we look at where the solar's connected, we look at the feeder exit, we look at the end of the line, any large sensitive industrial customers, we look at sensitive loads, hospitals, customers that have complained about flicker problems in the past. These types of things are the sections that we're identifying in this analysis. And we take a couple other test points just to give us a good idea of what's going on across the whole feeder. So we run our steady state analysis, we record the voltages, we lock the load tap changer regulators caps because they're not going to be able to respond fast enough to correct this voltage problem. So this is what really drives a lot of the flicker is the regulator can't react. Then we rerun it with the solar in a different position. So if it was on, we turn it off and see what happens and what our voltage change is. Record the voltage and calculate our percent change and then determine whether or not we're okay with that. So here's an example that I calculated for one of ours where it shows we've got our different types of locations on the left side, final and initial voltage difference, and then our percent difference. And then that percent difference is evaluated against the IEEE flicker curve for acceptability. We assume 10 to 20 fluctuations per hour on a cloudy day. That's, again, a little bit conservative. For a partly cloudy day, you're not always going to see 20 dips per hour. You're not going to see 10. But as Brian said, we don't have any of these on our system right now. We don't have any experience with what flicker actually happens when you change some of these stuff. So in our modeling, we're being a little more conservative. That might start to loosen up as we get some of these online and we can kind of examine the impacts of them. But for right now, we want to make sure that when they plug in and turn this thing on, it doesn't cause problems for the rest of our customers. That's really our obligation in all of this. So we incorporate several conservative assumptions to make sure that we catch it before it becomes a problem. Because again, if it becomes a problem, the only real answer is lowering the impedance, which is big line rebuilds, substation transformer replacements, things that get costly in a hurry. So again, we're trying to catch all of these on the front end so that we can find good spots for these solar installers to put their stuff in. So here's our flicker curve. You can see at the bottom is dips per hour. The left side is what percentages. And then you got the borderline of visibility and the irritation. At 20 dips per hour, it's at about 2.5%. So that's the criteria that we use. Anything over 2%, we kind of start looking at and determining whether it's okay based on what types of customers are on there, what types of loads, past history, those types of things. So that's our flicker process. That's really the most objectionable part of it, where we find the most problems, is in the flicker section. As you get 5-10 miles out from the substation, you start to see voltage changes of 5, 8, 10%, which is not good. Any industrial customers in the room know you can't really handle a 10% voltage swing very well. Your lights start to go up and down, those types of things. So that's really what we're trying to catch in all this, is specifically the flicker problems. Some of the other stuff is a pretty cheap fix if we don't catch it afterwards. But we don't want to be blinking everybody's lights all the time just to get some solar panels on the grid. So the last piece is the system protection piece. So during a fault on our primary, so if we have, let's say somebody hits a pole and the conductors wrap together, a squirrel gets across the primary on a transformer, we call that a fault. Basically, it's a non-load that creates a lot of current, usually in the order of several thousand amps on the 12 kV. The solar contributes about 120% of its nameplate. So if it's a 2 megawatt installation, it contributes about 100 amps worth of fault current into our 3, 4, 5,000 amp fault. So from the protection side, everything